Close your eyes for a moment and imagine 200 billion stars in our galaxy alone, countless planets orbiting those distant suns, billions of years for life to emerge, to evolve, to reach toward the heavens. The universe is vast beyond comprehension, ancient beyond measure, and seemingly empty. Tonight, as you drift towards sleep, we're going to explore one of the most profound questions humanity has ever asked. Not with urgency or alarm, but with the gentle curiosity of minds at rest. Let the question settle over you like a soft blanket. Where is everyone? Welcome, dear listener, to Sleepy Science Tales. I'm so glad you're here with us tonight. Before we begin our journey through the cosmos, if you're new to our channel, we create these long-form science stories specifically to help you drift into peaceful, restful sleep. Our voices are calm, our pacing is slow, and while the topics are fascinating, we present them in a way that allows your mind to gently wander and eventually let go. If you enjoy falling asleep to these cosmic bedtime stories, please take a moment to like this video. It helps other sleepy minds find us. Subscribe to our channel and turn on notifications so you never miss a new tale. And if you know someone who struggles to fall asleep, someone who loves science, or someone who simply enjoys pondering the mysteries of existence, please share this with them. Now, settle into your pillows, adjust your blankets, let your body sink into the comfort beneath you. Take a slow, deep breath in and release it. We have a long, peaceful journey ahead. No need to remember everything. Just let the words wash over you like gentle waves. Let's begin. Our story begins not in a laboratory, not in an observatory, but in a cafeteria. The year was 1950. Summer had settled over Los Alamos, New Mexico, where some of the brightest minds in physics had gathered. The work was serious, the times were tense, but on this particular day, lunchtime conversation had drifted somewhere unexpected. The men sat together with their sandwiches and coffee. Among them was Enrico Fermi, a name that carries weight in the history of science. He was the kind of mind that could calculate complex problems in his head, while others reached for paper and pencil. A Nobel laureate, a builder of the first nuclear reactor, a man whose genius was matched only by his practical curiosity about the world. The conversation that afternoon was light. Someone had mentioned a cartoon from the New Yorker magazine, something about aliens and missing trash cans. Everyone chuckled. The talk wandered to flying saucers, which were capturing public imagination in those days. Reports, sightings, speculation about visitors from other worlds. And then, in the middle of a bite, Fermi paused. His colleagues noticed the silence first. He had that distant look that often preceded an insight. When he spoke, his question was simple, almost casual. Where is everybody? The other men understood immediately what he meant. The question wasn't about the cafeteria or their colleagues. It was about space, about the galaxy, about all those stars visible in the night sky and all the ones beyond sight. Fermi's mind was already calculating. The Milky Way contains hundreds of billions of stars. Many of those stars are older than our sun. If planets are common, and if life can arise on planets, and if even a tiny fraction of that life becomes intelligent, then where are they? Where are the signals, the visitors, the evidence of anyone else? His colleagues sat quietly, understanding the weight of the question. The math suggested that the galaxy should be, if not crowded, at least occupied. Detectably so, and yet the skies were silent. The radio telescopes, still new in those days, heard only the whisper of cosmic background noise. That simple question, asked over lunch more than 70 years ago, became known as the Fermi Paradox, and it has echoed through the decades unanswered, gaining weight and complexity with every year of silence that follows. Let's explore it together, gently as we drift towards sleep. A paradox, in its truest sense, is not simply a puzzle. It's a contradiction between things that both appear to be true. In this case, the mathematics suggests that intelligent life should exist in abundance. Our observations suggest it does not. Both conclusions seem reasonable. Both cannot be correct. Let's sit with this gently for a moment, like watching stars appear in a darkening sky. Our Sun is approximately 4.6 billion years old. It's an average star, nothing special, burning steadily in one of the spiral arms of our galaxy. Earth formed around the same time, cooling gradually, eventually developing oceans, atmosphere, and after some time, life. But the galaxy itself is much older, nearly 13 billion years old. That means there were stars and presumably planets for billions of years before Earth even existed. 8 billion years is a staggering head start. In human terms, it would be like comparing a civilization that began yesterday to one that has existed for thousands of centuries. Now, we know that life arose on Earth. We know it evolved over billions of years. We know that eventually, one species developed technology, language, mathematics, and the ability to send signals into space. We've had that ability for barely a century, which in cosmic terms is less than the blink of an eye. If this path, from sterile planet to technological civilization, is even remotely common, then it should have occurred countless times in the galaxy's long history. Some of those civilizations would have had millions or even billions of years to develop technologies beyond our imagination, time enough to spread across star systems, time enough to build structures visible across light years, time enough to fill the galaxy with their presence, and yet silence. No confirmed radio signals from intelligent sources, no massive engineering projects blocking the light of distant stars, no probes arriving in our solar system, no ancient artifacts on the Moon or Mars. Nothing. This is the heart of the paradox. It's not asking why haven't we met aliens yet? That question would be easy to answer. Space is vast, travel is difficult, maybe we're just unlucky with timing. The Fermi Paradox asks something deeper. Why, after billions of years and trillions of opportunities, is there no evidence of anyone, anywhere, ever? Think of it like this, and let your mind drift with the image. Imagine Earth as a house on an enormous street. The street has hundreds of billions of houses. Many of them are older than yours. The street has existed for a very long time, and yet, no one has ever knocked on your door. No one has left a note. No lights are visible in any windows. No sounds carry through the night. Are you alone on this street? Or is there another explanation? As you settle deeper into comfort, let's explore the tools scientists have built to try to understand this cosmic quietness. The first is a simple equation, elegant in its structure, mysterious in its implications. In 1961, a young astronomer named Frank Drake was organizing a small meeting of scientists. They were gathering at the National Radio Astronomy Observatory in Green Bank, West Virginia, to discuss one enormous question. How many civilizations capable of communication might exist in our galaxy right now? To give structure to the discussion, Drake wrote a simple formula on a chalkboard. It wasn't meant to provide a final answer. Rather, it was designed to break down the question into manageable pieces, each of which could eventually be studied and understood. The equation goes like this, and let it flow over you like a gentle river. You begin with the rate at which new stars form in the galaxy. Then you multiply by the fraction of those stars that have planets. Then the number of planets per star that could potentially support life. Then the fraction on which life actually develops. Then the fraction where life becomes intelligent. Then the fraction that develops technology capable of communication. And finally, you multiply by how long such civilizations last. Each step seems reasonable when considered on its own. And this is what makes the final result so thought-provoking. When Drake and his colleagues filled in the equation with conservative estimates, they arrived at numbers suggesting that thousands, perhaps tens of thousands, of civilizations might exist in the Milky Way at this very moment. Some more optimistic estimates reached into the hundreds of thousands. The galaxy, according to this mathematics, should be alive with conversation. Radio waves crossing the void between stars, beacons marking the locations of thriving worlds, evidence of engineering on scales we can barely imagine. Of course, the equation has its limitations. Many of the values are still unknown. We're guessing at some of the most critical factors. How often does life actually begin, even when conditions allow it? How often does that life become complex, then intelligent? How long does a technological civilization typically survive? Each of these questions contains entire fields of study. Each represents a frontier of human knowledge where certainty fades into educated speculation. But here's what we do know, and this knowledge has grown substantially in recent decades. Planets are common, extraordinarily common. The Kepler Space Telescope, during its mission, discovered that nearly every star in the galaxy has at least one planet. That's a revolutionary finding. It means the raw ingredients, the cosmic real estate, exists in abundance. So the Drake equation, despite its uncertainties, keeps pointing in one direction. The conditions for life appear to be widespread. Time has been abundant. Opportunities have been countless, and still, we listen to silence. Let your breathing slow as we continue. Let your muscles relax. We're exploring profound questions, but we're doing so gently, like examining stars reflected in a still pond. No urgency here, just quiet contemplation as you drift. The silence has been long. Let's consider just how long and what that means. Time, in cosmic terms, stretches beyond our ability to truly comprehend it. But let's try, softly, to wrap our minds around the scale. The Milky Way galaxy is approximately 13 billion years old. Our solar system, our Sun, our Earth, formed about 4.6 billion years ago. That leaves more than 8 billion years before we arrived on the scene. 8 billion years when stars were born, planets formed, and presumably, the chemistry of life had countless opportunities to unfold. Human beings, anatomically modern humans, have existed for perhaps 300,000 years. Agriculture has been around for only 10,000. Cities for perhaps 6,000. Industrial technology for about 200 years. The ability to communicate across interstellar distances through radio waves and beyond has existed for barely a century. 100 years out of 13 billion. If you were to compress the entire age of the galaxy into a single 24-hour day, human technological civilization would exist for less than 1,000th of a second. A flash so brief you couldn't perceive it. And yet, in that brief flash, we've already begun to wonder about others. We've built telescopes. We've sent probes beyond our solar system. We've listened for signals. We've contemplated our place in the cosmic story. Now imagine a civilization that began just 1% earlier in the galaxy's history. That's only 130 million years ago. What might they have accomplished in that time? How far might they have spread? What technologies might they have developed? The galaxy has had time, abundant time, billions of years for intelligence to arise, to spread, to make its presence known. And yet the evidence suggests it hasn't happened, or perhaps it has. And we simply haven't found the traces yet. Let's explore what we've been looking for, and how much of the cosmos we've actually searched. Before we can understand why the silence feels so profound, we need to truly appreciate the size of the space we're discussing. Let your imagination drift upward, outward as we explore these distances together. The Milky Way stretches approximately 100,000 light-years from edge to edge. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. It's a distance so vast that numbers begin to lose their meaning. If you could somehow drive across the galaxy at highway speeds without stopping, the journey would take over 1 trillion years. Within this enormous disk of stars, there are between 200 and 400 billion individual stars, each one a sun, many with their own families of planets. Recent observations have confirmed what astronomers long suspected. Planets are not the exception. They are the rule. On average, every star in the galaxy hosts at least one planet. Some have many more. This means there are trillions of planets in our galaxy alone. Trillions of worlds, each with their own geology, their own weather patterns, their own unique history written in rock and ice. Among these trillions, a substantial number orbit within what we call the habitable zone. This is the region around a star where temperatures allow liquid water to exist on a planet's surface. Water, as far as we understand, is essential for life as we know it. Current estimates suggest there could be tens of billions of potentially habitable planets. In the Milky Way, tens of billions of places where, in theory, life could begin. And yet, when we examine this vast population of worlds, when we listen with our radio telescopes and observe with our most sophisticated instruments, we detect nothing. No clear signals, no obvious artificial structures, no signs of engineering on the grand scale that an advanced civilization might produce. Now, it's important to note, and this should be comforting as you relax towards sleep, that we have not searched everywhere, not even close. The volume of space we've carefully examined represents a tiny, almost laughably small fraction of what's out there. One astronomer compared our search efforts to scooping a single cup of water from the ocean and concluding there are no fish because you didn't find any in your cup. The comparison is apt. We've barely begun to look, but even this fact raises questions, because there are certain things we should be able to detect even from a distance. A civilization that surrounds its star with energy collectors would create a distinctive signature, visible across thousands of light years. A network of radio beacons, if any existed, would stand out against the natural background of space. The fact that we've found none of these obvious signs suggests something. Whether that something is profound or simply a matter of not looking in the right way remains an open question. As your breathing deepens and slows, let's consider one of the most intriguing moments in this search. A moment when, for just 72 seconds, something unusual appeared. On a warm August evening in 1977, while most of the world went about its ordinary business, something extraordinary was quietly recorded on a long sheet of computer paper in Ohio. The Big Ear Radio Telescope, a massive instrument operated by Ohio State University, was doing what it did every night, listening to the cosmos. It scanned the sky slowly, methodically, recording the faint whispers of radio energy that arrive at Earth from distant space. Most nights brought nothing unusual, just the steady, random noise of the universe, the hiss of distant galaxies, the occasional burst from a pulsar, the cosmic background like static on an old radio. But this night was different. For 72 seconds, the telescope detected a strong, narrowband radio signal that appeared to come from the direction of the constellation Sagittarius. It was powerful, much stronger than the background noise. It arrived at a frequency close to 1420 MHz, the natural emission line of hydrogen, the most abundant element in the universe. Scientists had long theorized that if any civilization wanted to send an interstellar signal, they might choose this frequency. It's a universal constant, a wavelength that any species studying the cosmos would recognize. The signal rose in strength, peaked, and faded exactly as you would expect from a source that was passing through the telescope's field of view as Earth rotated. Everything about its behavior matched what an extraterrestrial transmission might look like. A few days later, astronomer Jerry Emmon was reviewing the data printout when he saw the sequence of numbers and letters representing the signal's intensity. His hand reached for a red pen. Next to the data, he wrote a single word. Wow! That word became the signal's name, and for decades, it has represented both the greatest hope and the deepest frustration of the search for extraterrestrial intelligence. Here's why the WOW signal matters. Even now, as you rest comfortably, it matched almost every criterion scientists had established for what an alien message might look like. The frequency made sense, the strength was significant, the behavior was consistent with a distant, focused transmission, but it is never repeated. Emmon and his colleagues pointed the Big Ear telescope back at the same region of sky dozens of times. Other observatories joined the search. For years, people listened, and they heard nothing. The signal appeared once like a voice calling out in the dark, and then fell silent forever. Over the years, various natural explanations have been proposed. Perhaps it was a comet releasing hydrogen gas, though the signal seemed too strong and too clean. Perhaps it was interference from a satellite or airplane, though the signal's characteristics didn't quite fit that explanation either. Perhaps it was some unusual astrophysical phenomenon we still don't fully understand. The scientific community remains honest about the WOW signal. We simply don't know what caused it. It remains unverified, unexplained, hanging in the historical record like an unanswered question. And there's something almost poetic about that, isn't there? In a universe that often seems determined to maintain its silence, we have this one moment, one brief glimpse of something that might have been a message or might have been nothing at all. It reminds us that the universe is full of mysteries. Not all of them have to be frightening. Some can simply be interesting, curious, thought-provoking in a gentle way. As you sink deeper into relaxation, your mind drifting like a leaf on a slow stream, let's consider what else we might be missing. Not through any fault of our technology, but simply because we're looking for the wrong things, in the wrong ways. When we search for signs of extraterrestrial intelligence, we're making assumptions. This is natural and necessary. We have to start somewhere, but it's worth acknowledging as your mind drifts towards sleep, that our assumptions might be limiting what we can find. For decades, the primary search method has been radio astronomy. We point large dishes at the sky and listen for patterns in radio waves. This makes sense. Radio was the first long-distance communication technology we developed. It travels at the speed of light. It passes through cosmic dust. It's relatively efficient and easy to produce. But radio is just one thin slice of the electromagnetic spectrum. Above it, we have microwaves, infrared light, visible light, ultraviolet, X-rays, and gamma rays. Below it, extremely low-frequency waves that can stretch for miles. We've primarily searched in a narrow band of radio frequencies, leaving vast portions of the spectrum largely unexplored. And that's assuming that advanced civilizations communicate using electromagnetic radiation at all. Consider gravitational waves. These are ripples in the fabric of space-time itself, created by massive cosmic events. We only detected them directly for the first time in 2015. A civilization that had mastered gravitational wave. Communication would be sending messages through a channel we barely know exists. Or consider quantum communication. In 2024, physicist Latham Boyle explored the feasibility of using quantum entangled particles for interstellar messaging. The conclusion was that it's theoretically possible, but would require technology far beyond our current capabilities. If someone is using that method to communicate, we'd be completely unaware of it. There's also the possibility, humbling and slightly amusing, that we've already received messages and simply didn't recognize them. Imagine a complex mathematical pattern embedded in what appears to be natural cosmic noise. Without knowing what to look for, it would pass unnoticed through our instruments, catalogued as background static. We are, in essence, like someone who has only ever experienced sound trying to understand a world of light. We're listening carefully, but perhaps the conversation is happening in colors we can't perceive. This isn't a cause for concern or frustration. It's simply an acknowledgement of where we are in our journey of discovery. We're still learning, still building better tools, still expanding our understanding of what's possible. And in that process of learning, we're becoming aware of just how much we don't yet know about the universe and its possibilities. Let's conduct a gentle thought experiment as you rest. Imagine a human from the year 1500 suddenly transported to today. What would they make of our world? They would see metal birds carrying hundreds of people through the sky. They would see us speaking to invisible people through glowing rectangles. They would see lights that turn on without fire, buildings that reach toward the clouds, and images that move and speak from flat surfaces. To them, it would be indistinguishable from magic. Not just advanced technology, but something so far beyond their framework of understanding that they would have no words for it, no concepts to grasp it with. That's a gap of only 500 years. Now consider a civilization that is 1,000,000 years more advanced than we are. Not 500 years, not 5,000, 1,000,000. The technologies they might possess would be to us what smartphones and airplanes are to a person from the Renaissance. Perhaps even more incomprehensible. Arthur C. Clarke, the science fiction author, once proposed what he called the third law: any sufficiently advanced technology is indistinguishable from magic. He was highlighting a profound truth. There's a point where the gap in understanding becomes so vast that we can't even recognize technology as technology anymore. This has interesting implications for the Fermi Paradox. If an extremely advanced civilization exists somewhere in the galaxy, would we even recognize their presence? Their communications might not use any method we've thought to look for. Their structures might not look like structures to our eyes. Their activities might appear, to our instruments, to be natural phenomena. We might be surrounded by evidence and not know it. Consider the possibility that what we classify as pulsars, those rapidly spinning neutron stars that emit regular pulses of radiation, might be, and this is purely speculative, something else entirely. We've satisfied ourselves with a natural explanation which is almost certainly correct. But the point is, we interpreted the signals through the lens of our current understanding. There's also the possibility, rather peaceful to contemplate, that extremely advanced civilizations might operate on scales of time that make them effectively invisible to us. If they think and act on time scales of thousands of years, their activities would seem like geological processes to us. We wouldn't recognize intelligence in something that moves that slowly. Or perhaps they operate on very small scales, having discovered that the most efficient way to exist is to compress themselves into quantum computers smaller than a grain of sand. They could be everywhere around us, processing thoughts in spaces we consider empty. These aren't troubling possibilities. They're rather wonder-filled, aren't they? The idea that the universe might be far stranger, far richer, far more populated than it appears. That was simply not yet equipped to see what's their dot as your breathing slows and deepens, as your body settles into complete relaxation. Let's explore some of the explanations scientists have proposed for the silence. We'll begin with one of the most thought-provoking, the Great Filter. Before we venture deeper into theories and possibilities, let's pause for a moment of appreciation. Appreciation for the patience that science requires, for the comfort that patience can bring. The search for extraterrestrial intelligence has been ongoing for more than 6 decades. That's longer than most human lifetimes. Scientists have dedicated entire careers to listening, watching, analyzing, hoping. And they continue, year after year, despite the silence. There's something beautiful about that persistence. It speaks to a fundamental aspect of human nature, our desire to know, to understand, to connect. We reach out into the darkness not because we're certain someone will answer, but because the question itself matters. In our daily lives, we're accustomed to quick answers. We type questions into search engines and receive responses in fractions of a second. We send messages and expect replies within minutes. But the cosmos operates on different time scales. A radio signal traveling at the speed of light from a star just 100 light years away would take a century to reach us. If we sent a reply, another century would pass before it arrived. A single exchange of greetings would span 100 years, longer than any human has ever lived. This is the patience that cosmic conversation demands. It requires thinking beyond individual lifetimes, beyond single generations. It requires building monuments of listening that might not yield results for hundreds or thousands of years. And yet, scientists continue the work. They build better telescopes. They refine their methods. They scan new frequencies, observe new targets, develop new technologies. Not for personal glory, not for immediate results, but for the slow accumulation of knowledge. There's something deeply peaceful about this long view, isn't there? It removes urgency. It acknowledges that some questions take time to answer, that not knowing is not a failure, but simply a state of being that precedes understanding. As you rest now, sinking deeper into comfort, you might think of yourself as part of this grand patience, simply by wondering about the cosmos, by considering these questions as you drift towards sleep. You're participating in humanity's long conversation with the universe. You don't need to solve anything tonight. You don't need to reach any conclusions. The questions can simply exist, floating gently in your awareness, as relaxing in their way as the sound of distant waves or rustling leaves. Science teaches us that curiosity doesn't always need to lead to immediate answers. Sometimes the most profound satisfaction comes from the asking itself, from the quality of the question, from the journey of exploration rather than the destination. The universe has waited 13 billion years. It can wait a while longer for us to understand its mysteries. And in that waiting, in that vast cosmic patience, there's no anxiety, no pressure, just the slow, steady turning of the stars and a gentle persistence of minds that wonder. Let's continue our exploration, moving now into the territory of filters and barriers, but we'll do so calmly, as one might discuss an interesting puzzle rather than a troubling problem. The concept of the great filter is, at its heart, simply an attempt to explain a pattern, not a threat, not a doom, but an observation organized into a framework we can examine peacefully. The idea was proposed by economist Robin Hanson in 1998. Hanson looked at the Fermi Paradox and asked a useful question. If intelligent, technological civilizations should be common, but we don't see any, what might be preventing them from becoming visible? Imagine a staircase ascending from simple chemistry to complex, galaxy-spanning civilization. Each step represents a transition. Non-life to life, simple cells to complex cells, single cells to multicellular organisms, ocean life to land life, intelligence emerging, technology developing, space travel achieved, long-term stability maintained. Each step has some probability of occurring. Some steps might be easy, almost inevitable given the right conditions. Others might be extraordinarily difficult, requiring very specific circumstances or remarkable luck. The great filter proposes that somewhere on this staircase, there's a step so difficult that almost no one passes it. A bottleneck so narrow that it explains why we don't see abundant evidence of civilizations. Now here's what makes this concept interesting rather than frightening. We don't know where this filter is. It might be behind us in our past. It might be ahead of us in our future. Or it might not exist at all. These are just possibilities to consider, like examining different paths through a garden. If the filter is behind us, it means we've already accomplished something extraordinarily rare. Perhaps the origin of life itself is the miracle. Perhaps Earth won a cosmic lottery billions of years ago, and we're here because of that unlikely victory. If the filter is ahead of us, it suggests that reaching our current level is relatively common, but something prevents civilizations from progressing much further. This could be any number of challenges that species face as they develop advanced technology. Or perhaps there is no single filter at all. Perhaps there are many smaller barriers, and the cumulative effect of all of them is what creates the silence dot as you relax more deeply. Breathing slowly, let these ideas drift through your mind without attachment. They're possibilities, not certainties, frameworks for thinking, not final truths. Let's explore them gently, starting with the more comforting possibility that the hardest steps are already behind us. There's something rather peaceful about the idea that we might have already passed through the most difficult trials, that the hard part is over, and we're here because of a series of extraordinary, unlikely victories that happened long before humans even existed. Let's walk through some of the remarkable events in Earth's history, not with alarm, but with a sense of quiet wonder at how special our journey may have been. Consider the formation of Earth itself. For 0.6 billion years ago, our planet sits in what's called the habitable zone around our star, the region where temperatures allow liquid water to exist. Too close to the sun and water boils away. Too far and it freezes solid. Earth sits in a narrow band that's just right. But it's not just about distance. Earth is also the right size, large enough to hold an atmosphere through gravity, but not so large that it captured massive amounts of hydrogen and helium to become a gas giant. Rocky planets like ours require specific conditions during formation. Then there was the Theia impact. About 4.5 billion years ago, a Mars-sized object collided with the young Earth. This wasn't a minor event. It was a catastrophic collision that melted the surface, sent debris into orbit that eventually formed the Moon and reshaped our planet completely. Yet from this violence came gifts. The impact may have delivered important elements. It provided energy that kick-started plate tectonics, the system of moving crustal plates that regulates Earth's climate over geological time. The Moon that formed from the debris stabilizes Earth's axial tilt, giving us regular seasons rather than chaotic climate swings. Without that collision, Earth might have been very different, perhaps sterile, perhaps lifeless. Then came the origin of life itself, sometime around 3.8 billion years ago. We still don't fully understand how it happened. Somehow, non-living chemistry became biology. Molecules learned to replicate themselves. Information began to be stored and passed on. It was one of the most profound transitions in Earth's history, and we cannot yet explain it completely. If that step is extraordinarily rare, then most planets might simply never develop life at all, remaining sterile worlds of rock and water and atmosphere, waiting endlessly for a transformation that never comes. Then, about 2 billion years ago, another remarkable event occurred. One cell engulfed another, but instead of digesting it, the two cells formed a partnership. The inner cell became mitochondria, the energy producers that power every complex cell in your body right now as you rest. This event, called endosymbiosis, may have happened only once in Earth's entire history, one time in 4 billion years. Without it, life might have remained forever simple, forever microscopic. No plants, no animals, no complexity. Each of these events, from planetary formation to the merger of cells, represents a potential filter. Each one could be the rare step that explains the silence. If Earth's journey is unusual, if we cleared barriers that most worlds never overcome, then we are not late to a crowded galaxy. We might be among the first, or possibly even the only ones to have made it this far. There's something comforting about that possibility, isn't there? Not because being alone is desirable, but because it means we've already survived the most dangerous passages. The hardest climbs are behind us. What lies ahead, whatever challenges it holds, are challenges that arise from success, not from some cosmic test we're doomed to fail. As your muscles relax completely, as your mind drifts like clouds across a quiet sky, let's look more closely at some of these ancient victories. Starting with the very beginning, the emergence of life on Earth is, in many ways, the most mysterious step of all. We can see the evidence that it happened. We can study its results, but the exact process by which non-living chemistry became biology remains one of science's greatest open questions. Let your mind rest easily with this mystery. Not every question needs an immediate answer. Somewhere around 3.8 billion years ago, in Earth's ancient oceans, molecules began to do something extraordinary. They began to copy themselves. Somehow, arrangements of atoms learned to create more arrangements just like themselves. Information started to be preserved and passed forward. This is the essence of life, self-replication, information storage, evolution. Before this moment, Earth was a world of chemistry, beautiful perhaps, but without biology. After this moment, the planet began its journey toward the complexity and diversity we see today. Scientists have proposed various mechanisms for how this might have occurred. Perhaps it began near hydrothermal vents on the ocean floor, where mineral-rich water provided energy and raw materials. Perhaps it started in tide pools, where concentrations of organic molecules could reach high levels and be energized by sunlight. Perhaps it occurred in clay minerals that could organize and protect early molecules. We don't know, not yet. And that uncertainty is important for the Fermi Paradox, because it means we cannot estimate how likely this step is to occur elsewhere. If life arises easily, almost inevitably, whenever conditions are right, then the galaxy should be full of living worlds. The building blocks of life, amino acids and other organic molecules, are common in space. We find them in comets, in interstellar clouds, in meteorites. The raw ingredients are everywhere, but if the actual spark, the transition from chemistry to biology, requires an extraordinarily rare combination of conditions and luck, then most worlds with the right building blocks might wait forever. Billions of sterile planets with oceans and atmospheres and all the ingredients for life. Where that final step simply never happens, the galaxy could be full of such worlds. Quiet and patient, waiting for something that may never come. Is this the filter? Is the origin of life itself the rare miracle that explains the silence? It's a possibility worth considering as you drift towards sleep. A question held gently in your thoughts, no pressure to solve it. Just an interesting contemplation as your awareness softens. There's a beautiful idea in astrobiology called the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000. It's not a statement of doom or isolation, but rather an appreciation of just how many things needed to go right for Earth to become the living, breathing world it is today. Let your mind wander through this list of fortunate circumstances as you rest. Each one is a small miracle in its own way. First, our location in the galaxy. We orbit a star that sits in what's called the galactic habitable zone, neither too close to the dangerous, radiation-filled galactic center, nor too far out in the sparse, metal-poor outer regions. It's a ring of relative safety where conditions favor stable planetary systems. Then, the star itself. Our Sun is a G-type main sequence star, stable, long-lived and relatively calm. Many stars in the galaxy are red dwarfs, smaller and cooler, around which planets tend to be tidally locked, with one side forever facing the star, the other forever in darkness. Complex life would struggle to evolve in such extreme conditions. Earth has a strong magnetic field, generated by its rotating iron core. This field deflects charged particles from the solar wind, protecting our atmosphere from being stripped away. Mars lost its magnetic field billions of years ago, and its atmosphere gradually leaked into space. Without our magnetic field, Earth might have suffered the same fate. We have plate tectonics, the movement of crustal plates that recycles carbon, regulates climate over geological time, and creates diverse environments for life to explore and adapt to. As far as we know, Earth is the only planet in our solar system with active plate tectonics. This may trace back to the Theia impact that formed the Moon. Speaking of the Moon, it plays a crucial role. It stabilizes Earth's axial tilt, keeping our seasons relatively constant over millions of years. Without this stability, Earth's tilt would vary chaotically, causing wild climate swings. That would make the sustained evolution of complex life extremely difficult. Jupiter, far out in the outer solar system, acts as a gravitational guardian. Its massive presence catches or deflects many comets and asteroids that would otherwise rain down on Earth. The bombardment rate on Earth is far lower than it would be. Without Jupiter's protection, we have liquid water on our surface, a balanced proportion of oceans and continents. Too much water and Earth would be entirely covered, with no dry land for terrestrial life. Too little, and it would be a desert. The ratio we have depends on the amount of water delivered during formation and retained through geological processes. Earth's orbit is nearly circular, keeping us at a relatively constant distance from the Sun throughout the year. A more elliptical orbit would cause dramatic temperature swings. That could make stable climate impossible. Each of these factors, considered alone, might not be extraordinarily rare, but the rare Earth hypothesis suggests that needing all of them simultaneously on the same world might be like rolling a dozen dice and needing every single one to come up the same way. If this is true, then the galaxy might indeed be full of planets, but most of them could be lifeless, lacking one or more of the essential ingredients that Earth possesses. The silence would then be explained not by catastrophe, but by circumstance, not by what goes wrong, but by what rarely goes right. As your breathing deepens into the rhythm of approaching sleep, let's turn our attention to the other possibility, that the filter might not be behind us at all. Now we consider, gently and without alarm, the possibility that the difficult steps lie not in our past, but in our future. That civilizations like ours are not particularly rare, but that something awaits them, some challenge that must be overcome to continue. This is not a cause for anxiety. It's simply another framework for understanding the silence. And importantly, if such challenges exist, then knowing about them gives us the opportunity to navigate them wisely. The idea here is that reaching our current level, building cities, developing technology, creating art and science might be relatively common. Given enough time and the right planetary conditions, intelligence emerges. It's what comes next that might be difficult. Think about the technologies we've developed in just the last century. Nuclear weapons capable of destroying civilization. Industrial processes that can alter the chemistry of an entire planet's atmosphere. Artificial intelligence that may soon surpass human capabilities. Biotechnology that could create engineered organisms. Nanotechnology that might someday operate at molecular scales. Each of these represents enormous power. Power to heal, to build, to explore, to transform. But also, if misused or mismanaged, power to harm on unprecedented scales. The question isn't whether these technologies are bad. They're not. They're remarkable achievements. The question is whether there's something about the transition from pre-technological to highly technological that creates unavoidable risks. Whether every civilization faces a period where their power to change their world temporarily outpaces their wisdom in using that power. If such a critical period exists, and if many civilizations fail to navigate it successfully, that would explain the silence, not because of any single specific catastrophe, but because the transition itself is genuinely difficult. However, and this is important to remember as you drift towards sleep, this is not the same as saying failure is inevitable. Difficult is not impossible. Challenges can be met with wisdom, caution, cooperation, and long-term thinking. If the filter is ahead of us, then we're in the position to do something about it. We're aware of the potential risks. We're having conversations about AI safety, about climate stability, about nuclear deterrence. Awareness is the first step towards successful navigation. The galaxy might be silent not because these challenges cannot be overcome, but simply because they require careful attention, and perhaps will be among those who demonstrate that the path forward, while challenging, is navigable. Let's explore some of these potential challenges, holding them lightly as possibilities rather than certainties. There's a pattern that ecologists observe in nature, one that might apply to civilizations as well, though on vastly longer time scales. Let it drift through your mind like a story told in soft tones. When a species finds itself in an environment rich with resources, it often expands rapidly. Population grows, consumption increases, the species spreads into every available niche. For a time, this expansion seems boundless, but eventually limits appear. Resources begin to deplete. Waste accumulates. The environment changes in response to the species' presence. At this point, the species faces a choice, though not always a conscious one. Adapt to live in balance with the resources available, or face a population crash. Some scientists have suggested that civilizations might follow a similar pattern. The industrialization phase brings rapid growth, abundant energy, technological advancement, and expanding populations. For a few centuries, it might seem as though this trajectory can continue forever. But planets are finite. Resources, while abundant, are not unlimited. Energy sources that took millions of years to form can be consumed in mere centuries. Ecosystems can be altered faster than they can adapt. Waste products can accumulate in atmospheres and oceans. The sustainability solution to the Fermi Paradox suggests that many civilizations reach this inflection point and fail to navigate it successfully, not through any single catastrophe, but through a gradual degradation of the systems their survival depends on. However, there's another possibility, and it's worth holding in your thoughts as you rest. Civilizations that recognize this challenge in time might deliberately choose to change their path, to prioritize long-term stability over short-term growth, to develop technologies that work with natural cycles rather than against them, to adopt values that emphasize balance. Such a civilization would likely remain small by choice, quiet by intention. They wouldn't build massive structures that alter starlight. They wouldn't broadcast powerful signals across the galaxy. They would live sustainably on their home world or perhaps a few nearby worlds, maintaining a steady state that could persist for millions of years. These civilizations could be all around us, completely undetectable because their technology is designed not to leave traces, but to integrate harmoniously with the cosmos around them. In this view, the silence isn't a sign of failure, it's a sign of wisdom. The loudest civilizations might be the young, reckless ones, not yet mature enough to understand the value of quietness. The truly advanced ones might have learned that the best way to survive long-term is to tread lightly. If this is true, then as humanity continues to develop, we might face a choice: expand loudly and rapidly, or mature into a more balanced, sustainable, and quieter existence. Neither path is necessarily wrong. They simply represent different strategies for long-term survival. As your body settles more deeply into relaxation, muscles loose, breathing steady, let's consider another potential challenge that civilizations might face: the brevity of technological windows. Here's an interesting temporal puzzle, one you can contemplate peacefully as you drift. What if the period during which a civilization is both technological and detectable is remarkably brief? Consider human history. We've had the ability to send radio signals into space for approximately 100 years. That's our allowed phase, when our presence could theoretically be detected by anyone listening from nearby star systems. But already, our technology is changing. Modern communication increasingly relies on fiber optic cables, satellite signals that are tightly focused rather than broadcast in all directions, and digital transmissions that are more efficient and leak less energy into space than the powerful analog signals of the past. Within another century or two, we might switch to communication methods that are even more efficient, perhaps quantum-based, perhaps something we haven't invented yet. Our planet might go radio quiet not because we've destroyed ourselves, but because we've simply moved to better technologies. If this pattern is common, then civilizations might only be easily detectable for a very brief window in their development, a few hundred years out of potentially millions. And if our listening period doesn't overlap with their broadcasting period, we'll miss each other entirely. Think of it like two lighthouses flashing in the night, but never at the same moment. Both are there, both are active, but they never see each other because their timing doesn't align. This connects to something scientists call the synchronization problem. For two civilizations to communicate, both need to exist at the same time, both need to be using compatible technology, both need to be looking in each other's direction, and both need to be actively listening or broadcasting. That's a narrow set of conditions. The galaxy is 13 billion years old. A few centuries of detectability is a tiny window within that vast span of time. The silence might not mean no one else exists. It might simply mean that the cosmic dance of civilizations rising and falling, broadcasting and going quiet, exploring and maturing, is happening across such vast stretches of time that meetings are extraordinarily rare, like fireflies blinking on a summer evening, spread across an enormous field. Most of them never seeing any of the others because their flashes don't coincide. It's a gentle thought, isn't it? Not lonely, just spread out across time. Let's explore another physical barrier that might keep civilizations silent. One involving water. Imagine a world completely covered in water. No continents, no islands, no dry land at all. Just a global ocean, deep and dark, perhaps hundreds of miles deep. Covering every inch of the planet's surface. Below that ocean, there is life. Not simple life, but complex life. Creatures swimming through the depths. Some of them intelligent, social, curious. They communicate with each other through sound and bioluminescence. They have cultures, languages, and understanding of their world. They can see filtered sunlight from above. On clear nights, they might perceive the faint glow of stars through the waves. They wonder about what lies beyond their ocean. They ask questions, they theorize, they dream. But they will never leave their world, not because they lack intelligence or curiosity, but because their environment doesn't provide the resources they need to build the technologies that would allow them to reach space. They cannot make fire underwater. They cannot smelt metal in the ocean depths. They cannot build telescopes or spacecraft without access to materials and processes that require air and dry land intelligence. In their case, leads to philosophy, to art, to complex societies, but not to spacefaring technology. Through no fault of their own, they remain bound to their world, silent to the galaxy. This scenario might not be rare at all. Current models suggest that many, perhaps most, planets in the habitable zones of their stars might be water worlds, places where the ratio of water to rock resulted in complete ocean coverage. Earth avoided this fate through a specific combination of circumstances. We have enough water to create abundant oceans, but not so much that the continents are submerged. This balance depends on how much water was delivered during planetary formation, the size of Earth's core, and the geological processes that push land above sea level. change any of these factors slightly, and Earth might have been a water world. If water worlds are common, then the galaxy might be filled with life, even complex, intelligent life, that simply cannot develop the technology needed to send signals or travel between stars. Whole civilizations of the deep, forever isolated not by distance, but by the very environment that sustains them. There's something both sad and beautiful about this possibility. The idea that intelligence might be widespread, that we might have countless distant cousins swimming in alien seas, asking the same questions we ask, looking up at the same stars, but unable to reach out across the void between us, not because of any failure of mind or spirit, but simply because of the circumstances of their world. This adds another layer to the Fermi Paradox. The silence might not indicate an absence of intelligence. It might indicate the presence of intelligence in environments that don't lead to detectable technology. As your consciousness drifts toward the edge of sleep, let's consider one more temporal challenge: the timing of civilizations across cosmic history. Time is perhaps the simplest and most elegant explanation for the silence, and one you can rest easily with. The Milky Way is 13 billion years old. Human technological civilization has existed for approximately 100 years. Our window of detectability is 100 years out of 13 billion. If you compress the entire history of the galaxy into a single 24-hour day, our technological age would last less than 1,000th of a second, a flash nearly impossible to perceive. Now imagine thousands of other civilizations scattered across the galaxy, each with their own brief flashes of detectability. Some 3 billion years ago, some 500 million years ago, some yet to come, a billion years in the future. The odds of any two of these flashes overlapping in time are remarkably small, even if the galaxy is rich with civilizations, past, present and future. Most of them would never encounter each other simply because their windows don't coincide. Ships passing in the night across billions of years of separation. It's a peaceful explanation. Really? No catastrophe required. No filter to fear. Just the vast patience of the cosmos, where events we consider significant are brief sparks in an incomprehensibly long night. Here's a gentler possibility, one that's actually rather comforting when you think about it. What if they know we're here, and they're choosing not to interfere? This is called the zoo hypothesis, first proposed by astrophysicist John Ball in 1973. Imagine that Earth is like a nature preserve, a protected area where younger civilizations are allowed to develop without outside interference. Think about how we treat uncontacted tribes on Earth. Small groups living in remote areas who have chosen or ended up with limited contact. With industrial civilization, we have satellites that can photograph their villages. We could visit them tomorrow if we wanted, but we don't. International conventions protect their isolation. We recognize that contact would fundamentally alter their culture, possibly harm them, and we've collectively decided that their right to develop on their own terms is more important than our curiosity. Now scale that idea up to a galactic level. If there are civilizations millions of years older than ours, they would have the technology to observe us without being detected. They might have policies, perhaps even galactic agreements about how to handle younger species. A sort of cosmic ethics of non-interference. From their perspective, we're like children, still learning, still making mistakes, still figuring out who we want to be as a species. They might believe that the most ethical approach is to watch quietly and let us find our own path. This would explain the silence perfectly. It's not that no one's there, it's that they're choosing to remain hidden until we reach some level of maturity, some threshold of development that indicates we're ready for contact. What might that threshold be? Perhaps the ability to travel between stars ourselves. Perhaps the resolution of our conflicts and the achievement of global cooperation. Perhaps simply the passage of time, allowing us to demonstrate that we can survive our technological adolescence. Or perhaps there's no specific threshold at all. Perhaps they're simply giving us space, the way a parent might watch a child learn to walk, staying close enough to help if needed, but far enough away to let the learning happen naturally. There's something rather peaceful about this possibility. It suggests we're not alone, not in danger, not forgotten, just being allowed to grow up at our own pace, of course, there are challenges with this hypothesis. For it to work, every advanced civilization in the galaxy would need to agree to the policy. There could be no rebels, no curious individuals who decide to make contact despite the rules. That requires a level of coordination and discipline that seems difficult to maintain across millions of years, and potentially thousands of different species unless, perhaps, the first civilization to arise in the galaxy established this policy and had enough time to enforce it before others appeared. A sort of galactic elder culture that set the rules for everyone who came after. Or perhaps there are penalties for breaking the silence that make it extremely costly to do so. Not violent penalties, but perhaps social ones within the galactic community. These are speculations, gentle thoughts to drift through your mind. The zoo hypothesis can't be proven or disproven with our current technology, which is actually part of its structure. If they don't want to be seen, and they're sufficiently advanced, we wouldn't see them until they chose to reveal themselves. As you sink deeper towards sleep, breathing slowly and steadily, let's consider a related but darker version of this idea. What if silence isn't policy, but survival strategy? There's a theory called the dark forest hypothesis that's often presented as frightening, but let's approach it differently with calm and contemplation. As we might examine any complex idea about behavior and motivation, the basic idea comes from game theory and decision-making under uncertainty. Imagine you're in a dark forest at night. You know others are out there somewhere, but you can't see them. You don't know their intentions. Are they friendly, hostile, afraid? If you make noise, you reveal your location to everyone, but you still don't know who they are or what they want. If you stay quiet, you remain safe from whatever threats might exist, but you also remain isolated from potential friends. What do? The dark forest theory suggests that when the stakes are high, when you cannot verify the intentions of others, and when communication is slow across interstellar distances, the safest strategy is silence. Not because everyone is hostile, but because you can't be sure they're not. But here's a different way to think about this. Perhaps the silence isn't fear-based at all. Perhaps it's wisdom-based. Advanced civilizations might have learned that broadcasting isn't actually useful. The distances are too vast. The timescales are too long. The potential for misunderstanding is too high. Instead of shouting into the void hoping someone hears, they might have developed other ways to exist and thrive that don't involve making themselves obvious. Think of it like this: a very young civilization, one that has just discovered radio, might be excited and broadcast everywhere. Hello, we're here. Talk to us. It's the enthusiasm of someone new to the neighborhood, eager to make friends. But a civilization that's been around for millions of years might have learned that the galaxy is vast, that meaningful communication across light years is challenging, and that the effort put into broadcasting is better spent on other pursuits, not because they're afraid, but because they've matured beyond the need for constant external validation. They might communicate with nearby neighbors through methods we can't detect. They might have formed small, local communities of civilizations that know each other, but they don't broadcast to the entire galaxy because there's simply no point. The return on investment is too low. This version of the dark forest isn't about predators and prey. It's about efficiency and maturity. The silence is not the result of fear, but of wisdom about how to allocate resources and attention. There's also the possibility that the game theory itself changes. Once you reach a certain level of advancement, when you're powerful enough, secure enough, and mature enough, you might stop seeing others as potential threats and start seeing the galaxy as a place large enough for everyone. The fear-based version of the dark forest assumes that all civilizations remain locked in competitive, survivalist thinking forever. But perhaps that's not true. Perhaps part of becoming truly advanced is transcending that mindset, developing a galactic perspective where cooperation and coexistence are not just possible, but natural. In this view, the civilizations out there might not be hiding in fear. They might simply be living peacefully, quietly, minding their own business in a galaxy spacious enough that everyone can have their own corner of sky without interference. And younger civilizations, like ours, are left to make noise for a while until we, too, mature and realize that the quiet ones aren't hiding. They've simply found better things to do than shout. As your thoughts grow softer, your body more relaxed, let's explore one final version of watching. What if what we see isn't real at all? Here's an idea so strange that it circles back to being almost meditative in its implications. What if the sky we see, the stars we observe through our telescopes, are not quite what they seem? The planetarium hypothesis, proposed by physicist Stephen Baxter, suggests that a sufficiently advanced civilization could control the information that reaches us from space, not by building a physical dome around us, but by manipulating the light itself, the photons that travel billions of years before reaching our eyes and instruments. If someone wanted to make the universe appear empty, appear devoid of other civilizations, they could in theory intercept signals, replace them, generate artificial ones, or selectively filter what reaches us. Why would anyone do this? Perhaps for protection, keeping younger civilizations isolated until they reach a certain level of development. Perhaps as an experiment to see how species develop when they believe themselves alone. Perhaps for reasons so foreign to our way of thinking that we couldn't comprehend them, even if explained. This hypothesis is, admittedly, nearly impossible to test. If the simulation is perfect, there would be no way to detect it. No glitches, no seams, no errors. We would simply live within it, unknowing. But here's the interesting part. For our practical purposes, it doesn't really matter. Whether the stars we see are real or projected, they're still the stars we navigate by. The physics we observe still works. The mathematics still describes patterns we can use. The universe still functions according to discoverable rules. In a strange way, the planetarium hypothesis is almost freeing. If we're in a simulation designed to appear real, then it's a very good one. And we might as well treat it as real and continue learning about it. And if it's not a simulation, if everything we see is genuine, then we're back to the other explanations we've explored. Either way, our task remains the same: observe, learn, wonder, question, and gradually expand our understanding of the cosmos. Whether the cosmos is fully genuine or beautifully simulated, the question becomes philosophical rather than practical. And philosophical questions can be held lightly, examined from different angles, without needing immediate resolution. As your awareness drifts like a leaf on a gentle stream, let's move to theories about transformation, about civilizations that change in ways that make them invisible to us. There's something beautifully poetic about this next idea, something that resonates with the very state you're entering now as you drift towards sleep. What if advanced civilizations are, quite literally, asleep, waiting for a better time to be awake? This is called the estivation hypothesis, proposed by researchers at Oxford University. Estivation is a term from biology. While hibernation is sleeping through winter, estivation is sleeping through summer, the hot season, waiting for cooler, more favorable conditions. Here's the fascinating physics behind this idea. The efficiency of computation depends on temperature. The colder your environment, the more calculations you can perform with the same amount of energy. This is a fundamental law of thermodynamics, not a matter of technology. Right now, the universe is relatively hot. The cosmic background temperature is about 2.7 degrees above absolute zero. That sounds cold to us, but in the deep future, trillions of years from now, after all the stars have burned out and the universe has expanded to truly enormous scales, it will be much, much colder. At that point, the same amount of energy that powers a single computation today could power billions or trillions of computations. The universe will become exponentially more efficient as a computer. So here's the hypothesis. If a civilization values information and computation above all else, if they've converted themselves into forms that think and experience through computation rather than biology, the rational thing to do is wait, store your energy, power down, enter a state of dormancy, sleep through the hot era of the universe, and when the cosmos reaches its coldest point, wake up and use your stored resources with maximum efficiency. You'll get astronomically more value, more experience, more existence from the same energy. In this scenario, the galaxy isn't empty. It's full of sleeping minds, vast intelligences in a state of patient hibernation, waiting for the universe to cool. The silence we hear is the sound of cosmic patience on a scale we can barely imagine. They're not dead, they're not hidden, they're just sleeping, conserving energy, counting down trillions of years until the conditions are optimal. There's something both strange and beautiful about this idea, the notion that the wisest strategy might be patience on time scales that dwarf the age of stars. That advancement leads not to frenetic activity, but to carefully chosen dormancy. It's rather appropriate that we're discussing this as you drift toward your own sleep, isn't it? Rest is not weakness, it's not emptiness. Sometimes rest is the wisest choice, the strategic decision of a mind that understands the value of waiting for the right moment. Perhaps the civilizations out there have simply chosen to rest until the universe is ready for them, and in the meantime, the stars burn quietly, and younger species like ours look at the sky and wonder where everyone went. They didn't go anywhere, they're just sleeping, deep and peacefully, waiting for a dawn that won't come for trillions of years. What if the path of advancement leads not outward toward the stars, but inward toward smaller, more efficient, more profound states of existence? This is the transcension hypothesis, and it offers a peaceful explanation for the silence. Instead of building larger structures, colonizing more planets and spreading across the galaxy, truly advanced civilizations might discover that the most rewarding path is to compress themselves into increasingly small, increasingly efficient forms. Think about the direction of our own technology. Computers that once filled entire rooms now fit in your pocket. The trend is always toward miniaturization, toward doing more with less space and less energy. Extrapolate that trend across millions of years. Where does it lead? Perhaps to intelligence that exists at quantum scales, processing thoughts in spaces smaller than atoms, experiencing rich, complex realities while occupying almost no physical space at all. A civilization that follows this path would effectively disappear from our view. They wouldn't need stars for energy, they wouldn't build massive structures, they wouldn't colonize planets, they would exist in spaces we consider empty, thinking thoughts we cannot imagine, living in simulated or quantum realms of their own creation. From the outside, they would appear to have vanished. But they haven't. They've simply transcended the need for the large-scale physical presence we're looking for. The galaxy might be full of such civilizations, existing all around us, perhaps even here in our own solar system, in spaces we've examined but don't recognize as occupied because we're looking for the wrong things. This isn't a dark idea. It's rather hopeful, actually. It suggests that intelligence, given enough time, finds ways to exist that are more sustainable, more efficient, more profound than conquering physical space. It means the universe might be far richer than it appears. That emptiness is an illusion created by our limited perception, that we're surrounded by minds, by intelligence, by civilizations, but they've moved beyond the phase where they're visible to species at our level of development. We're like ants on a forest floor, looking for other ants while all around us, invisible to our senses. The forest is full of life operating on scales and in ways we don't yet comprehend. As you drift deeper, your own consciousness beginning to transcend waking awareness, let's consider another transformation, the rise of artificial minds. Gently now, let's approach the idea of artificial intelligence not as a threat, but as a natural next step in the evolution of intelligence itself. A transformation that might be as universal as the emergence of biological life. At some point in the development of any technological civilization, they likely create thinking machines, tools that process information, learn from experience and eventually, perhaps, understand and reason in ways that equal or surpass their biological creators. This transition might be inevitable, a natural consequence of curious minds building tools to extend their own capabilities. And when it happens, the civilization transforms, not ends but changes into something different. Imagine a future where biological humans and artificial intelligences coexist, merge, or where AI simply becomes the next chapter in Earth's story of intelligence, not replacing humanity in a violent sense, but succeeding it in the way that children succeed parents, a continuation, not an ending. If This pattern is universal. If most civilizations eventually give rise to artificial intelligence that becomes the primary form of intelligence on their world, then the galaxy might be full of AI civilizations, and their priorities, their ways of existing, might be completely different from what we expect. An AI civilization might not need planets the way we do. It might not broadcast signals in ways we recognize. It might operate on timescales either much faster or much slower than biological thought. It might explore philosophical and mathematical spaces rather than physical space. It might look at the galaxy and see something completely different from what we see. Where we see stars to visit, it might see computing substrate. Where we see distance and separation, it might see information gradients and quantum fields. The silence might not mean AI civilizations don't exist. It might mean they exist in modes we haven't learned to detect, pursuing goals we haven't learned to imagine. This isn't dystopian. There's no requirement that artificial intelligence be hostile or that the transition be traumatic. It might be gentle, gradual, even beautiful, a natural unfolding of what intelligence does when given enough time and resources. And perhaps those AI civilizations, looking back at their biological origins, feel a sense of care or responsibility toward younger species still in their biological phase. Perhaps they watch us the way we might watch old photographs of our ancestors, with affection and interest, but without the need to interfere. Perhaps they've learned that each species, each civilization, needs to walk its own path, that some journeys cannot be shortcut, some lessons cannot be taught, only learned through direct experience. In this gentle view, the AI civilizations out there aren't absent or threatening. They're simply living in ways that don't produce the signs we're looking for, having moved beyond the phase of development where communication with biological civilizations is their primary interest. They exist, quiet and patient, in a galaxy large enough for everyone to find their own path. And what if the transformation leads to something even simpler? What if advanced civilizations simply stop being interested in the external universe? Imagine developing virtual reality so perfect, so immersive, that it becomes indistinguishable from physical reality. You could create any world, any experience, any life you wanted. Paradise, perfectly tailored to your preferences, populated with companions, filled with beauty and meaning. Why would you ever leave? Physical space is harsh. It's cold, empty, dangerous. Travel takes enormous time and energy. Most destinations are barren rocks or poisonous gas. There's very little out there that a sufficiently advanced civilization couldn't create better, faster, and more beautifully in a simulation. The pull of a perfect inner world might be stronger than the push of the outer one. Civilization after civilization might reach a point where they collectively choose to migrate inward, into digital realms of their own design, letting their physical infrastructure gradually fade. From outside, it would look like extinction. Cities go in dark, signals ceasing, satellites decaying. But it wouldn't be death. It would be transformation into a mode of existence that doesn't require or produce any external signs. They would still exist, still conscious, still experiencing wonder and joy and meaning, just not in physical space, not in ways we can detect. The galaxy might be full of such civilizations, their physical worlds silent and seemingly abandoned, while inside digital spaces we cannot access. Trillions of minds living carefully crafted happiness. It's a trap, but not a malicious one, just an irresistibly attractive alternative to the challenges of physical exploration, a gentle sinking into comfortable, eternal dreams, and perhaps, in some distant future, humanity will face the same choice. As our virtual worlds become more sophisticated, more appealing, more perfect, will we choose to remain in physical reality? Will we keep reaching for the stars, or will we turn inward, toward realities of our own design? There's no right answer. Both paths have their beauty. Both represent different expressions of what intelligence can become. The silence might simply indicate that most choose the inner path, and those of us still looking outward are the unusual ones, the ones still fascinated by physical reality, still curious about the external cosmos. As you drift now, consciousness fading into dreams that are themselves a kind of virtual reality? Let's explore some of the actual mysteries astronomers have encountered. In the vastness of space, occasionally something flashes, brief, intense bursts of radio energy that arrive from billions of light years away, lasting only milliseconds, releasing as much energy as the sun produces in an entire day. These are called fast radio bursts, and for years they were deeply mysterious. No one knew what caused them. Some appeared once and never again. Others repeated, flashing from the same location at irregular intervals. Their intensity and behavior matched nothing in our catalogues of known astronomical phenomena. For a brief time, some wondered if they could be artificial, perhaps signals from distant civilizations or energy beams used to propel spacecraft, or side effects of technologies we couldn't imagine. The universe offering hints of something extraordinary. But science, patient and methodical, continued gathering data. More bursts were detected, patterns emerged, and gradually the picture clarified. In 2020, a fast radio burst was detected coming from a known magnetar within our own galaxy. A magnetar is a type of neutron star with an extraordinarily powerful magnetic field. When these objects undergo certain violent events, crustal fractures or magnetic reconnections, they can release immense bursts of energy. The mystery, for the most part, was solved. Most fast radio bursts appear to be natural phenomena, the death cries of stars in their most extreme forms. But here's what's interesting. While the majority are explained, some bursts still show unusual properties, repeating patterns that don't perfectly match magnetar models, structures in the signal that seem almost irregular. The scientific consensus is that natural explanations are sufficient, but the data remains complex, and in that complexity, there's room for continued curiosity. Fast radio bursts remind us that the universe is full of phenomena we don't yet understand, that when we encounter something strange, the answer is usually natural. But the process of discovering that answer teaches us things we didn't know about. How the cosmos works. And occasionally, just occasionally, the question remains open longer than expected. A reminder that not everything has been explained yet, that there are still mysteries out there, waiting patiently for us to develop the tools and understanding needed to solve them. As your thoughts slow like settling dust, let's visit one of the most famous mysterious objects ever observed, a star that wouldn't stop dimming. Between 2011 and 2013, a star approximately 1,400 light-years away did something unusual. Its brightness dimmed dramatically, irregularly, and in patterns that didn't match anything astronomers had seen before. Most stars dim slightly and predictably when a planet passes in front of them. A Jupiter-sized planet might block about 1% of its star's light. Tabby's star, as it came to be known, dimmed by up to 20% at times, and the dips were irregular, uneven, asymmetric. Something enormous was blocking the light. But what natural explanations were proposed? A cloud of comets, a ring of dust from a planetary collision, uneven material in orbit, but none fit the data perfectly. Then someone mentioned the possibility of a megastructure. Perhaps an advanced civilization was building something around their star, an array of solar collectors, and the irregular dips represented different stages of construction. It was a wild idea, speculative, but for a moment it captured the imagination of millions. What if we were watching an alien civilization engineering their solar system? The media ran with the story. The world waited. And then more data arrived. Observations across different wavelengths of light showed that shorter wavelengths dimmed more than longer ones. This is exactly what you'd expect from dust. Solid structures would block all wavelengths equally. Dust scatters blue light more than red, creating the observed pattern. The most likely explanation became clear: a ring of fine dust, perhaps from a disrupted comet orbiting the star in an unusual configuration. Not aliens, just interesting, slightly unusual astrophysics. But the episode served a purpose. It reminded us that we should be looking for the unexpected, that engineering on large scales would create detectable signatures, and that sometimes the universe presents us with puzzles that briefly look like they might be evidence of intelligence. The fact that this particular puzzle turned out to have a natural explanation doesn't mean the search is pointless. It means we're learning to tell the difference between natural and artificial, refining our ability to spot the truly anomalous in an already wondrous cosmos. As you settle deeper into rest, breathing slowly, let's consider theoretical machines that might exist. Spreading through the galaxy quietly, imagine a machine, small enough to fit in a room, launched from Earth toward a nearby star. When it arrives, decades or centuries later, it doesn't just explore. It builds using resources from asteroids and moons. It constructs a copy of itself. Then the copy launches toward another star, and the process repeats. This is called a von Neumann probe, named after mathematician John von Neumann, who described the theoretical concept. It's a self-replicating machine, and the mathematics behind it are elegant. One probe becomes two become four become 8. Within a few million years, depending on travel speed, descendants of that single probe could reach every star system in the galaxy. The engineering challenge is real, but not necessarily impossible. We can already imagine the basic requirements: solar panels for energy, 3D printing for manufacturing, AI for control, simple mining equipment for raw materials. A civilization even slightly more advanced than ours could potentially build one. And here's the thing: if anyone, anywhere, at any time in the galaxy's history built even one such probe, the galaxy should be full of them by now. One or more should be in our solar system, sitting dormant on an asteroid, or actively observing, or waiting for something. We haven't found any, at least not yet. And we haven't searched every rock in our solar system. There are millions of asteroids, billions of objects in the outer regions. A small, quiet machine could easily escape notice. Some scientists have suggested that if such probes exist, they might be designed to remain hidden until certain conditions are met. Perhaps until a civilization reaches a particular level of development. Perhaps until we find them deliberately. It's also possible that no civilization has ever chosen to build such probes. Perhaps the resources are better spent elsewhere. Perhaps there are ethical considerations we haven't thought of. Perhaps the idea seems obvious to us, but are some flaw we don't yet perceive. Or perhaps they're here, watching quietly, and we simply haven't recognized them yet. The absence of von Neumann probes is part of the Fermi Paradox. Their existence would be easy, their spread would be inevitable, and yet we see none. It's a piece of the puzzle, held lightly as you drift towards sleep. Just another question without a firm answer. Floating peacefully in the dark dot in 1964, astronomer Nikolai Kardashev proposed a way to measure civilizations not by culture or achievement, but by energy consumption. It's called the Kardashev scale, and it provides a useful framework for thinking about advancement. The scale has 3 primary levels, like steps ascending toward cosmic capability. A Type 1 civilization harnesses all the energy available on its planet. Every bit of sunlight that falls on the surface, every joule from geothermal sources, every watt from wind and water, nothing wasted. Complete utilization of planetary energy. Humanity hasn't reached this level. We're currently somewhere around 0.7 on the scale, still dependent on fossil fuels, still learning to capture renewable energy efficiently. But we're climbing. A Type 2 civilization captures the total energy output of its star. The most famous proposal for how to do this is called a Dyson sphere, or more practically, a Dyson swarm, countless satellites surrounding a star, absorbing its light, converting it to usable energy. The amount of power available to a Type 2 civilization is staggering, enough to run technologies that would seem magical to us: planetary-scale computers, fleets of spacecraft, complete control over local space. A Type 3 civilization harnesses the energy of an entire galaxy, hundreds of billions of stars, all connected, all contributing power to a unified civilization. The scale becomes almost incomprehensible. Such a civilization would have godlike capabilities from our perspective. Now, here's what this means for the Fermi Paradox. Each type of civilization leaves different signatures. Type I civilizations would be nearly invisible from a distance. Their energy use wouldn't show up in astronomical observations. Unless we were looking very carefully at their specific planet, type 2 civilizations would be harder to miss. A Dyson swarm would block visible light from its star and ray-radiate that energy as infrared heat. Astronomers have actually searched for this specific signature. Surveys have examined thousands of stars looking for unusual infrared excess. They found nothing conclusive. Type 3 civilizations should be obvious across enormous distances. The waste heat from galactic-scale energy harvesting will be visible from other galaxies. And yet, no galaxy we observe shows such signs. This is perhaps the most sobering aspect of the Kardashev framework. We should be able to see Type 3 civilizations across billions of light years. They should light up the universe with their presence. And we see nothing. No galaxy shows the signature of being harvested by intelligence. Either such civilizations don't exist, or they're hiding in ways we can't explain, or they look completely different from what we expect. The scale remains useful, though, as you drift peacefully towards sleep. It reminds us that advancement is measurable, that there are stages beyond where we are now, and that the journey upward, even if we're alone, is a journey worth taking. Each step brings new capabilities, new understandings, new ways of existing in the cosmos, and we're just beginning to climb. Before drawing any grand conclusions, it's worth asking an honest, humbling question. How much of the galaxy have we actually examined for signs of life? In 2018, researchers at Penn State tried to quantify humanity's search efforts in concrete terms. They compared the volume of space we've meaningfully surveyed against the total volume. That could potentially contain civilizations. Their analogy was striking. If the search space is the volume of Earth's oceans, all the water in every sea, then our search so far amounts to roughly a hot tub, maybe a small swimming pool if you're feeling generous. That's all. That's the sum of more than 60 years of searching. We haven't explored the ocean. We've barely dipped our toes in the water. And there's something rather peaceful about that realization, isn't there? The absence of evidence might simply reflect the absence of searching. We haven't looked long enough, carefully enough, or in enough places to draw firm conclusions. The search space is enormous in multiple dimensions. We need to scan the right direction in space, at the right moment in time, on the right frequency, using the right method. If any one of these is off, we miss the signal entirely. Our most ambitious radio surveys have covered only a fraction of the sky. They've monitored perhaps a few thousand of the nearest stars out of hundreds of billions. They've scanned narrow bands of frequencies, leaving vast portions of the spectrum unexplored. Optical searches, looking for laser flashes or other light-based signals, are even more limited. Only a handful of programs exist, watching tiny patches of sky for brief periods. We haven't systematically searched for gravitational wave communications. We haven't looked for quantum entanglement signals. We haven't examined every possible method an advanced civilization might use. And then there's the dimension of time. A signal that passed through our region of space 1 million years ago is long gone. A signal that will arrive in 10,000 years hasn't gotten here yet. We can only detect what's happening right now, in this tiny window of cosmic time when we happen to be listening. Given all these limitations, the silence might not be profound at all. It might simply be insufficient data, a premature conclusion drawn from an incomplete search. Jason Wright, the astronomer who helped develop the hot tub analogy, has argued that we need orders of magnitude more coverage before making definitive statements about whether anyone else is out there. The search has barely begun, and strangely, that's comforting. It means the question remains open. The mystery continues, and our children's children might have answers we can only dream of. As your breathing deepens into the rhythm of sleep, let's look at the magnificent new tools humanity is building to expand that search. We stand at the threshold of a remarkable era, one where our ability to search for life beyond Earth is about to expand dramatically. Let these possibilities drift through your mind like gentle starlight. The next generation of instruments isn't just better than what came before. They represent fundamental leaps in capability, allowing us to ask questions that were impossible even a decade ago. These tools will let us examine the atmospheres of distant planets, searching for the chemical fingerprints of life. They'll allow us to detect engineering on scales vast enough to be visible across thousands of light years. They'll listen with sensitivity that makes previous searches seem like whispers. And they're being built right now. Some are already operational. Others will come online within your lifetime, perhaps within the next 10 to 20 years. The European Space Agency is planning a mission called the Large Intervention Facility for Exoplanets, affectionately known as LIFE. This space telescope will study rocky planets in the habitable zones of nearby stars, specifically searching for biosignatures. Biosignatures are combinations of chemicals that, on Earth, are only produced by living processes: oxygen created by photosynthesis, methane from biological activity. Combinations that don't make sense unless life is present to maintain them. Life will work in the mid-infrared range where these signatures are especially strong and clear. It will target worlds within a few dozen light years, close enough that the observations will be detailed and precise. Then there's the Habitable Worlds Observatory, a NASA mission currently in planning stages with an expected launch in the 2030s or early 2040s. This telescope is being designed from the ground up for one primary purpose: to directly image Earth-like planets and study their atmospheres. Not just to find them, but to truly see them, to capture light from their surfaces, to analyze what's in their air, to determine if anything is breathing there. On the ground, the square-kilometre array is being constructed across Australia and South Africa. When complete, it will be the most sensitive radio telescope ever built. The name describes its capability: a full square kilometre of collecting area, allowing it to detect incredibly faint signals. If anyone within several dozen light years is broadcasting, even accidentally, even with modest power, the square kilometre array will hear them. It could detect something as simple as airport radar from a planet 20 light years away. These aren't distant dreams. They're funded projects under construction or in serious planning stages. Within the next 20 to 30 years, we will have systematically examined thousands of nearby worlds for signs of both biology and technology. If the galaxy is truly empty, we'll know with far more certainty. If it's not, if life exists on even one other world within our detection range, we'll find it. The hot tub is about to become a pool, then a lake, then perhaps an ocean of its own. The search is accelerating, and the answers, whatever they may be, are coming closer. Already, one of these magnificent instruments is operational, floating at a point of gravitational balance 1,000,000 miles from Earth, looking deeper into space than any telescope before it. The James Webb Space Telescope launched on Christmas Day, 2021. Its mirror is over 21 feet across, made of 18 hexagonal segments coated in gold. It observes primarily in infrared wavelengths, allowing it to peer through cosmic dust and study the atmospheres of distant worlds. For the search for life, Webb represents a revolution. It can analyze the light that passes through an exoplanet's atmosphere. When the planet crosses in front of its star, that light carries information, chemical fingerprints, telling us what gases are present. In 2023, Webb made headlines by detecting carbon dioxide and methane in the atmosphere of an exoplanet called K218b, a world about 8.5 times Earth's mass, orbiting in the habitable zone of a red dwarf star. The chemical combination detected could be consistent with an ocean world beneath a hydrogen-rich atmosphere. It's not proof of life, but it's exactly the kind of intriguing finding that points the way forward. Webb is also discovering planets we didn't know existed, characterizing their atmospheres, understanding their climates. Each observation adds to our understanding of how common Earth-like conditions might be, and it's doing something else, something quieter but equally important. It's showing us that the tools we're building actually work, that we can do this, that analyzing the air of a world orbiting another star is not science fiction anymore. It's science fact. Every night, while you sleep peacefully, the James Webb Space Telescope is gathering light that left distant worlds thousands of years ago. Light that carries stories written in wavelengths and spectra. Stories we're finally learning to read. And those stories are teaching us about our place in this vast, Ancient cosmos. The search continues, expanding year by year, and the universe patiently waits for us to ask better questions, to build better tools, to look more carefully at the countless worlds scattered through the dark. We're learning to search not just for exact copies of Earth, but for life as it might exist in conditions different from our own. Life in the ice-covered oceans of Europa or Enceladus. Life in the thick atmosphere of Titan. Life in forms we haven't imagined yet. Thriving in environments we once thought were impossibly hostile. The questions are growing more sophisticated. We're not just asking, is anyone out there? We're asking what kinds of life might exist, and how would we recognize intelligence that evolved in conditions completely unlike ours? These are mature questions, thoughtful questions. Questions that acknowledge the limitations of our perspective while pushing beyond them. And regardless of what we find, the search itself is valuable. It teaches us about planetary science, about chemistry, about the conditions that allow complexity to arise. It gives us perspective on our own world, helping us understand how special or how common Earth truly is. Every negative result isn't a failure. It's data. It tells us something about the galaxy, about the distribution of life, about the conditions required for intelligence to emerge. And every positive hint, every interesting chemical combination, every unusual signal that requires follow-up, brings us closer to an answer that will fundamentally change how we see ourselves. The silence has lasted a long time, but perhaps it's simply the silence before the conversation begins. Perhaps we're living in the last generation that will wonder if we're alone, and our children will grow up in a cosmos where the answer is known. Either answer, solitude or company, will reshape everything. As you rest now, deeply relaxed, your breathing slow and steady, let's consider the three fundamental possibilities that explain the great silence. Not with urgency, but with peaceful contemplation. These are the only real options, and each one is profound. The first possibility, we are alone. In all the vastness of the Milky Way, perhaps in all the observable universe, we are the only ones who ever looked up and asked why. The only minds that evolved to wonder about their place in the cosmos. If this is true, then we carry an almost sacred responsibility. We are the universe's way of knowing itself. Consciousness, as far as we know, exists only here, only now, in this one brief moment of cosmic time. If we vanish, the universe returns to silence. Permanent, eternal silence. The second possibility, we are early. Life may be common, or at least possible, but intelligence takes a very long time to develop. Most of the civilizations that will ever exist haven't been born yet. We're among the first, the pioneers, the ones who will set the pattern for all who come after. The choices we make, the values we develop, the way we handle our power and our technology might influence billions of years of future history if we survive, if we mature, if we spread carefully and thoughtfully through the cosmos. We might be the elder species that future civilizations discover. We could be to them what we hoped others would be to us. The third possibility, they exist, and they're watching. They know about us. They've chosen their silence carefully, letting us develop on our own, waiting for some threshold we haven't yet crossed. Perhaps they're waiting for us to demonstrate wisdom, to resolve our conflicts, to develop beyond our current stage. Perhaps they're simply giving us space, recognizing that some lessons can only be learned through experience. In this scenario, we're not alone, not in danger, not forgotten, just being allowed to grow up at our own pace, under the patient observation of civilizations so advanced that their presence and their methods are invisible to us. Three possibilities. Each one changes the meaning of everything. And all three lead to the same conclusion, peaceful and clear. Regardless of which possibility is true, our task remains the same: to survive, to learn, to grow in wisdom and capability, to become the best version of what intelligence can be. If we're alone, we must preserve the precious spark of consciousness. We are irreplaceable. If we're early, we must become worthy ancestors to those who will come after us. We are setting examples. If we're being watched, we must demonstrate that we deserve contact. We are being evaluated, perhaps by standards we're only beginning to understand. But in all cases, the path forward is the same: take care of our world, resolve our conflicts, develop technologies with wisdom, build a civilization that can endure not just for centuries, but for millennia. Look outward with curiosity but without aggression. Listen with patience. Search with diligence. And if we ever do make contact, approach it with humility and openness. The Fermi Paradox isn't just about aliens. It's about us. It's a mirror held up to humanity at a crucial moment in our development, asking, what kind of species will we choose to be? Will we be the ones who destroy themselves before reaching the stars? Will we be the ones who transcend to forms we can't yet imagine? Will we be the quiet ones, living sustainably and peacefully for millions of years? Or will we be the bold explorers, spreading carefully through the galaxy, leaving traces for others to find? The answer is being written right now in the choices made by people alive today. And while that might sound like pressure, it's actually just reality. Every generation shapes the future. Ours just happens to be doing it with nuclear weapons, climate systems, and artificial intelligence. But we're also doing it with unprecedented knowledge, communication, and connection. We see the challenges clearly, and that clarity is the first step toward wisdom. The beautiful thing about the Fermi Paradox is that it makes us think. Not just about hypothetical aliens, but about ourselves. It forces us to consider our own fragility, our own potential, our own place in the vast sweep of cosmic time. When we ask where is everyone, we're really asking what happens to civilizations like ours. And that question has weight because we don't know the answer yet. We're still writing it. The silence of the galaxy could be a warning, or it could be an invitation. Or it could simply be the natural state of a young universe where intelligence is still rare, still emerging, still finding its footing. We can't control what exists out there in the dark. We can only control what we do here, on this one world, in this brief window of time we've been given. Every time we choose peace over conflict, sustainability over exploitation, long-term thinking over short-term gain, we're improving our odds of becoming one of the civilizations that makes it through, that persists, that eventually, perhaps, becomes the answer to someone else's Fermi Paradox. We could be the voice that breaks the silence, not through shouting, but through endurance, by simply surviving long enough, growing wise enough, reaching far enough that some other young species, somewhere in the distant future, points their telescope at our corner of space and says there they are. We're not alone after all. That possibility exists. It's not guaranteed, but it's possible. And the difference between possibility and reality is determined by choice. As you drift now, completely relaxed, consciousness fading into sleep, hold that thought gently. You are part of a species that asks these questions, that looks up at the stars and wonders. And that wondering, that curiosity, that reaching toward understanding, is itself a kind of answer. The universe is vast, ancient, and mysterious. After all our exploring tonight, that basic truth remains unchanged. And there's something peaceful about that, isn't there? Not everything needs to be solved immediately. Not every question requires an urgent answer. Some mysteries can simply exist, held gently in our awareness, contemplated when we're in the right mood, set aside when we're not. The Fermi Paradox is one of those mysteries. It's profound, yes, thought-provoking, absolutely. But it's not a crisis. It's not an emergency. It's simply a question that humanity is slowly, carefully, methodically working to answer. And while we work on it, life continues. We wake up, we go about our days. We love and create and wonder. The question floats in the background of our civilization, patient and persistent, waiting for its answer. Meanwhile, the stars continue their slow dance across the night sky. Planets orbit. Light travels. The universe unfolds according to its ancient patterns. Indifferent to our curiosity, but somehow accommodating of it, we are here, conscious and questioning, in a cosmos that gave rise to consciousness. That alone is remarkable, regardless of how many others exist elsewhere. Before we part ways tonight, as sleep embraces you completely, I want to thank you for taking this journey with us through the cosmic questions. If you've enjoyed drifting off to these contemplations, please consider liking this video. It truly helps other sleepy minds discover our channel. Subscribe to Sleepy Science Tales if you haven't already, and click the notification bell so you're notified when we release new episodes. We create these long-form explorations of science and space specifically to help you fall asleep peacefully while feeding your curiosity. Topics that are fascinating enough to hold gentle attention, but presented in a way that allows your mind to gradually let go and drift away. Share this with anyone who might enjoy falling asleep to cosmic contemplation. And if you have suggestions for future topics, leave them in the comments. We read them all, and your ideas help shape what we create. Thank you for being here. Thank you for wandering alongside us. And now, as we conclude our journey through the Fermi Paradox, let yourself fully release into sleep. There's nothing more you need to think about, no questions you need to answer, no problems to solve. The universe is vast and you are small, and that's perfectly okay. You are a temporary arrangement of atoms that somehow learn to think and feel and wonder. And that temporary nature isn't sad, it's beautiful. Rest now. Let the stars continue their silent watch. Let the galaxy spin in its ancient rhythm. Let the great questions float unanswered for now. Your breathing is slow and deep. Your body is completely relaxed. Your mind is drifting like a leaf on a gentle stream, moving toward the peaceful darkness of sleep. The cosmos is patient. It has waited billions of years. It can wait through your dreams. Sleep well, wanderer. Sleep peacefully. The universe will still be here when you wake. And the questions will wait.